Hi, I'm Lauren White. In this lesson, we'll talk together about how to identify chiral carbons. Okay, chirality is a crucial point in organic chemistry. It will come up again and again. You'll even see it in things like biology and biochemistry, believe it or not, because our bodies are chiral environments. And this means that sometimes one chiral molecule will be active in our body and another chiral molecule isn't. So let's back up. Aside from all of this being very important, what does it all mean? Well, a chiral molecule is a molecule that has handedness. It's either right-handed or it's left-handed. And the word chiral comes from the Greek word for hands. And hands are sort of the classic example we use to explain this. So to be a chiral atom, the official way to say this is it's a molecule that is a non-superimposable on its mirror image. Well, that sounds really complicated, but let's use our hands as an example. So hold your hands out in front of you with your left and right thumbs pointed towards each other, like this. Now, your hands are, well, they're essentially the same, right? You have a pinky finger, a ring finger, a middle finger, an index finger, and a thumb on both hands. Now, I want you to take your left hand and put it directly on top of your right hand and line up your middle fingers on top of each other. Now, they don't look quite so much the same. Your hands are mirror images of each other. So in our image here, if you see this dotted line, we'll call that our mirror. You can see that the left hand is the mirror image of your right hand. But they're also not superimposable, meaning we could not lay them on top of each other and then match. So no matter how you rotated your left hand, it will never lie flat on top of your right hand such that all the fingers match up exactly. This is what we mean by a chiral molecule. So we can look at a molecule as well, just like we looked at our hands. These two carbons are both connected to a fluorine, a chlorine, a bromine, and a hydrogen. And they are mirror images of each other, just like your hands. But again, they're also not superimposable. No matter how I might rotate the one on the left, it will never look like the one on the right. Because if we think about it, let's say that we want to get this hydrogen over to the left side. Well, I can certainly spin this molecule around that way, but now bromine is on the right side of my molecule. This can all be really hard to do in your head. I'd suggest getting an organic chemistry molecule set and actually just making this molecule and spinning it around in your hand. So that's what a chiral molecule is. But how do we identify something as chiral? Well, we're looking for a chiral atom in that molecule. A chiral carbon for the purposes of organic chemistry. And it turns out they're easier to spot than you might think. To identify a chiral carbon, we're just looking for a carbon that is bound to 4 different substituent groups. It has 4 areas of electron density, so it will be sp3 hybridized, and it will have a tetrahedral molecular geometry. So no double bonds, no triple bonds, just 4 single bonds to different things, and you've got a chiral carbon. So let's look at some examples to make sure we can spot these in a molecule. Now, this molecule is big and it looks pretty intimidating, but we just need to look at the carbons and find which ones have 4 different attachments. And there are some things that just stick out to us that help us eliminate a lot of these really quickly. First, let's look for double bonds. A carbon that has a double bond coming off of it cannot be chiral. So this carbon here can't be chiral, and this carbon here can't be chiral. Another thing we can look for are carbons that have implied hydrogens, specifically carbons that have 2 or more implied hydrogens. So these carbons here that only have 2 lines drawn to them would have 2 implied hydrogens, and therefore they cannot be chiral because they don't have 4 distinct groups. So we can go ahead and mark all of these off because we know that they do not have 4 distinct groups and cannot be chiral. Now we've made our work much easier, so let's start attacking some carbons. Let's start in the bottom left. This carbon is attached to the carbon above it, which is attached to the top of the ring, the carbon to the bottom right of it that is attached to the bottom right of the ring, and it's attached to this hydroxide, but that's only 3. What are we missing? We're missing 1 implied hydrogen. So there are 4 distinct groups here, so this carbon is chiral. All right, let's go to the next one. So this carbon is attached to this carbon to its left, which is attached to the top of the ring, the carbon to its right, which is attached to sort of the next ring in line, this methyl group right above it, and this carbon with a double bond on it below it. That is 4 different groups. So this carbon also is a chiral carbon. All right, next one in line right here. We see that this one has a hydrogen below it. It has a carbon to its left that's attached to sort of that side of the ring. It has a carbon to its right, which is attached to this side of the ring. It has a carbon up above it attached to the top ring. Perfect. That is 4 different groups. So this carbon is also chiral. Let's keep moving down the line. We've got this one here. And just like you expect, it's attached to 3 carbons that go to different parts of the ring and a hydrogen above it, so it is also chiral. There are 4 different groups. Now we can look to the one directly to its right, and again, we have 3 carbons that go to different parts of the ring. We have a hydrogen. There are 4 distinct groups there, so this is also chiral. All right, now up 1 carbon. Again, we have 3 carbons connected to different places in the ring. We have a methyl group up above it. Still though, 4 distinct groups, so that is a chiral carbon. All right, moving along to the right, we are looking at this carbon right here. It's attached to 2 carbons in the rings. It's attached to a carbon off to its right, sort of in the straight chain part of the molecule, and also an implied hydrogen. So again, that's 4 different groups. This is a chiral carbon. Now let's keep moving down that straight chain. We've just got a couple more carbons to check. And looking at this carbon right here, we see that it's attached to the carbon before it in the chain, the carbon after it in the chain, a methyl group above, and remember there would also be an implied hydrogen there. So again, we have a chiral carbon. All right, let's check this one at the top. Now notice it is attached to the carbon before it, which is attached to this big long chain. Then it's attached to a methyl group on its top left and a methyl group on its top right. It has 2 methyl groups. It does not have 4 distinct groups. Remember, it also have an implied hydrogen, but either way, it can't be a chiral carbon since it has 2 methyl groups. The carbons on the end, since they are methyl groups, remember they're CH3, they have 3 hydrogens, so they're also not chiral. So altogether, we have 8 chiral carbons. Now though, you should feel more comfortable identifying chiral carbons in a molecule.